Welcome to G Fun Facts Online. To look at the night sky is to witness a monumental crime scene. Every star, every galaxy, every cloud of gas we can observe is made of matter. You, the chair you sit on, the air you breathe, it is all matter. Protons, neutrons, electrons. But the fundamental laws of physics, the elegant equations that describe the interactions of the subatomic world, tell us this should not be so. According to the standard model of particle physics, the Big Bang should have produced equal amounts of matter and antimatter. Matter and antimatter are perfect opposites. For every particle of matter created, an antiparticle with opposite charge and quantum numbers, but identical mass, should also arise. When they meet, they annihilate instantly, converting 100% of their mass into pure energy in the form of gamma rays. If the laws of physics were perfectly symmetrical, the early universe would have been a chaotic soup of creation and annihilation that eventually canceled itself out completely. The cosmos should be filled with nothing but light, a cold, empty bath of radiation. There should be no stars, no planets, and certainly no observers to wonder about it. Yet we exist. This is known as the Baryon Asymmetry of the universe. Roughly 13.8 billion years ago, for every billion particles of antimatter, the universe created 1,000,000,001 particles of matter. A tiny fractional imbalance, a symmetry violation, allowed that one extra particle to survive the Great Annihilation epoch. That survivor is everything we see today. The entire visible universe is essentially the leftover rounding error of the Big Bang. To understand why we are here, we must understand antimatter. But studying it is fiendishly difficult. It is the most volatile substance in existence, exploding upon contact with even a single atom of air. To probe its secrets, we must create it, slow it down, catch it, and hold it still in a bottle made of nothing but invisible fields. We must contain the uncontainable to answer the ultimate question: what is the difference between the mirror image and the reality? In physics, symmetry is not just an aesthetic concept. It is a conservation law. If a physical system behaves the same way after a transformation, we say it possesses a symmetry. The behavior of the subatomic world is governed by three discrete symmetries. First, there is charge conjugation, or C-symmetry. This operation swaps a particle for its antiparticle. It reverses electric charge and all charge-like quantum numbers. If the universe were C-symmetric, a laboratory built of antimatter performing an experiment would get the exact same results as a matter laboratory. Second is parity, or P-symmetry. This is spatial inversion, essentially looking at the universe in a mirror. For a long time, physicists believed nature couldn't distinguish left from right. Third is time reversal, or T-symmetry. This reverses the flow of time. If you film a billiard ball collision and play it backward, it still obeys the laws of physics. In 1957, the physics world was shocked when Chien-Shiung Wu demonstrated that the weak nuclear force violates P-symmetry. It turns out the universe is handed. Certain particles, like neutrinos, are only ever found spinning to the left. Later it was discovered that carbon monophosphide symmetry, the combination of swapping charge and flipping space, is also violated in the decay of particles called kaons. Despite these individual violations, there is one sacred trinity that has never been observed to break: CPT symmetry. This theorem states that if you simultaneously swap every particle for its antiparticle, reflect the universe in a mirror, and reverse the flow of time, the laws of physics must remain identical. This theorem is built into the very mathematical foundation of quantum field theory. If Captain is conserved, then a particle and its antiparticle must have exactly the same mass and exactly the same lifetime. This brings us to the crux of modern antimatter research. If we can find even the tiniest difference between the mass of a proton and an antiproton, or the frequency of light absorbed by hydrogen versus antihydrogen, we would prove that Captain is violated. This would break the standard model and potentially explain the matter-antimatter asymmetry. To find that difference, We have to manufacture the stuff. Deep beneath the border of France and Switzerland lies the only facility in the world capable of producing low-energy antimatter, CERN's Antimatter factory. Creating antimatter is actually the easy part. High-energy collisions produce it all the time. When protons smash into metal targets at near light speed, their kinetic energy converts into mass, spraying out showers of new particles, including antiprotons. The problem is speed. These newborn antiprotons are traveling at nearly the speed of light. To study them, or to trap them, we need them to be effectively stationary. Trying to catch a relativistic antiproton in a trap is like trying to catch a bullet with a butterfly net. This is where the antiproton decelerator, or AD, comes in. The AD is a unique machine. Unlike the Large Hadron Collider, which accelerates particles to higher energies, the AD is a decelerator. It takes the hot, wild antiprotons produced by the proton synchrotron and tames them. Through a series of magnetic kicks and electron cooling, where a beam of cold electrons absorbs heat from the hot antiprotons, the AD slows the particles down from nearly the speed of light to about 10% of the speed of light. Recently, CERN installed a new ring inside the AD hull called ELENA, or Extra Low Energy Antiproton. This hexagonal machine takes the antiprotons from the AD and slows them down even further to just 100 kilo-electron-volts. Before ELENA, experiments had to use thick degrader foils to slow particles down, a messy process that annihilated 99.9% of the precious antimatter before it even entered the trap. ELENA uses gentle electric fields to decelerate them efficiently, increasing the number of usable antiprotons by a factor of 10 to 100. It is the difference between drinking from a fire hose and filling a precision pipette. Once you have these slow particles, you face the containment challenge. Antimatter containment requires a vacuum better than deep space. If an antiproton hits a nitrogen molecule in the air, it annihilates instantly. Experiments typically operate at pressures trillions of times lower than atmospheric pressure. To achieve this, the entire metal apparatus must be heated to hundreds of degrees Celsius for weeks to drive out any gas atoms trapped in the metal walls. Then, the walls of the trap are cooled to liquid helium temperatures, about 4 Kelvin. At this temperature, any stray gas molecule that hits the wall freezes instantly, sticking to the surface and removing itself from the vacuum. But you cannot hold antimatter in a jar. It must hover, suspended by invisible forces. For charged particles like antiprotons, physicists use the Penning trap. It is the gold standard of containment. An electric field is applied using a series of gold-plated ring electrodes to push particles back to the center axially. However, you can't confine a particle in 3D with just static electricity due to Earnshaw's theorem. So a strong magnetic field is applied along the axis. This forces the charged particles to spiral in tight circles rather than flying out sideways. Inside a Penning trap, antiprotons can be held for incredibly long times. The base experiment has stored the same antiprotons for over a year. They are the loneliest, longest-lived antiparticles in the universe. Trapping antihydrogen, however, is infinitely harder. Antihydrogen is formed by mixing an antiproton and a positron. The result is a neutral atom. Neutral atoms have no electric charge, so they ignore electric fields. They are immune to the strong Lorentz force of the magnetic field. However, antihydrogen has a tiny magnetic moment. It acts like a minuscule bar magnet. If you place it in a magnetic field gradient, it will feel a very weak force. By creating a magnetic bathtub, a region where the magnetic field is lowest in the center and rises sharply in all directions, you can trap these neutral atoms. This is the Ioffe-Pritchard trap. The trap depth is pitifully shallow, about 0.5 Kelvin. This means if the antihydrogen atoms have kinetic energy corresponding to a temperature higher than 0.5 degrees above absolute zero, they simply fly over the magnetic walls and annihilate. This is why cooling is the single most critical technology in the field. When antiprotons arrive from the decelerator, they are still technically hot in terms of atomic motion. To trap them, we must cool them to cryogenic temperatures. Several methods are used. There is electron cooling, where heat transfers to light electrons which are then discarded. There is evaporative cooling, where the hottest particles are allowed to escape, leaving the remaining pool colder, much like blowing on coffee. And then there is sympathetic cooling, where laser-cooled ions like beryllium or magnesium are trapped alongside the antimatter to suck the heat out of it. The holy grail, however, was to laser-cool antihydrogen directly. In 2021, the Alpha collaboration achieved this. They tuned a laser to the Lyman alpha transition of antihydrogen. Every time an atom absorbs a photon, it receives a tiny kick of momentum. If the laser is tuned slightly below the resonance frequency, the atom only absorbs photons when moving towards the laser due to the Doppler shift. The kick slows the atom down. After absorbing and re-emitting thousands of photons, the antihydrogen atoms were cooled to sub-microkelvin temperatures. This allows for gravity measurements and spectroscopy of unprecedented precision. The AD hall at CERN is crowded with different experiments, each using distinct strategies to interrogate antimatter. First, there is Alpha, the master of spectroscopy. Their goal is to mix antiprotons and positrons to form antihydrogen, trap it, and blast it with lasers and microwaves. Their triumph was measuring the 1s-2s transition, essentially the color of antimatter, to 12 decimal places. Then there is BASE, the Baryon Antibaryon Symmetry experiment. They do not make neutral atoms. They keep single antiprotons in a penning trap to measure the magnetic moment. They hold the world record for the most precise comparison of matter and antimatter, measuring the antiproton's magnetic moment to 1.5 parts per billion. There is also AGES and GBAR, experiments dedicated to determining if antimatter falls up or down. GBAR creates antihydrogen ions which are easier to cool before stripping the extra positron to let the neutral atom fall. And while not in the AD hall, the LHCb experiment studies CP violation in heavy quarks, helping to map out the parameters of the standard model. We are looking for cracks in the mirror. Here is how we measure them. The transition of an electron from the ground state to the first excited state in hydrogen is one of the most precisely measured quantities in physics. Alpha measured this frequency in antihydrogen and found that the frequencies match to a precision of 2 parts in a trillion. This implies that Captain symmetry holds tight. The internal structure of the anti-atom is identical to the atom. BASE compares the frequency at which a proton and an antiproton orbit in a magnetic field, finding they are identical to 16 parts in a trillion. This is the most stringent test of Captain symmetry for baryons. Then there is the gravity test. Does antimatter have anti-gravity? General relativity says no. Gravity couples to mass, not charge. But some quantum gravity theories suggest slight deviations. In 2023, AlphaG released antihydrogen from a vertical trap and counted how many annihilated at the top versus the bottom. The observation was clear. It falls down. The acceleration of antimatter is consistent with Earth's gravity, within about 20% error margins. Future experiments aim to refine this to look for tiny deviations that could signal fifth forces. Beyond the lab, there are wild frontiers and medical applications. The ACE experiment at CERN investigated using antiprotons for cancer therapy. While protons deposit energy at a specific depth, antiprotons behave like protons until they stop, and then they annihilate. This releases an extra burst of energy directly into the tumor. Results showed antiprotons are 4 times more effective at killing cells than protons, though the cost currently makes it impractical. Then there is the dream of propulsion. Antimatter has the highest energy density of any substance. A few grams could power a ship to Mars in weeks. However, the reality is stark. It costs roughly $62 trillion to produce 1 gram of antihydrogen. Current accelerators are inefficient, and storing grams of antimatter is currently impossible due to the space charge limit in traps. We can store about 10 million antiprotons. To get 1 gram, we would need trillions of times more. Ultimately, The study of antimatter is a study of ourselves. We are the anomaly. We are the glitch in the matrix. The containment of antimatter represents the pinnacle of human engineering, holding the most destructive substance in the universe effectively motionless, cooling it to temperatures colder than the void between galaxies, and measuring it with the precision of a clock that loses a second every billion years. So far, the mirror seems perfect. The proton and the antiproton are identical twins, separated only by charge. CPT symmetry stands firm. And yet, the mystery remains. If they are perfect reflections, where did the antimatter go? The answer may lie in the next decimal point. It may lie in the behavior of neutrinos, or in a subtle violation of gravity, or in a dark sector of physics we have yet to touch. Until then, the physicists at the antimatter factory will keep working, trapping the ghosts of the Big Bang, looking for the tiny crack in the mirror that let the light of the universe in. Thanks for listening to G Fun Facts Online.